You know, there's a lot of engineering concepts in the real world. You just have to look hard enough.
Bro, just put the ball down. I want to play.
Don't you have that engineering test on the 20th? I bet you don't even know all the forces on this ball you're about to hit.
Bro, just like give me the ball. Come on, I just want to play.
Get it back when you're done studying.
Where am I right now? You got a haircut? What am I, Jackie? I got matcha? Who are these people? What am I doing here, bro? Can you say something?
Today, we're going to talk about statics.
What is statics, you asked? Well, statics is the branch of engineering mechanics that studies forces on objects in a state of equilibrium, meaning they are either at rest or moving at a constant velocity. Now, we'll try this practice problem. A beam with total length of 120 inches shown below has a pin reaction at point A and a roller reaction at point B. So this problem specifically is asking us to draw a free-body diagram, apply equilibrium in the horizontal direction to solve for the unknown horizontal forces, and then it's also asking us to apply equilibrium by summing the moments at about point A to solve for the unknown force at point B. And the final step that it's asking us to solve, apply equilibrium by summing forces in the vertical direction to solve for the unknown vertical forces at A. Now, I know that's a lot to take in, but first, let's start drawing the free body diagram. Do I have any volunteers?
Man, I ain't doing this.
Okay, well, I guess he's gone. Fahad, you can draw the free body diagram.
So to start off, let's talk about what we're given. So over here, we have vertical forces going down on the object, a force of 800, and right here we have a force of 1600. Additionally, we also have a pin reaction right here and a roller reaction right here. A pin reaction would mean that we have two forces acting on the object itself. So there would be one force, A of X, and A of Y. And here, at the roller reaction, we have a reaction of B of X. We're also given is the lengths in between all of the reactions. These are 30 inches, 50 inches, and 40 inches. And now that we know what we're given, we also have these variables, A of X, A of Y, and B of X, what we need to solve for. So these would be the unknowns of the problem.
Why does this even matter?
I'm glad you asked. Well, this question is a lot more realistic than you think. In the real world, bridges follow the exact same concepts with different reaction points on different ends, but one thing stays the same. Everything is at equilibrium.
Before we start solving, let's get some assumptions on the board. So because we're at an equilibrium problem, and we only have one horizontal force, A of X here, and the other side's a roller, we know that the two forces on either side have to come out to equal 0, which leaves the implication that A of X at equilibrium has to equal to the other force, which doesn't exist, meaning A of X is 0.
All right, so now that we have our knowns, our unknowns, and our assumptions listed, it's time for us to finally choose which equations we're using. For starters, because we're at equilibrium, we're gonna need the sum of all of our forces. We're gonna need the sum of all of our moments. And to find the moment, we also need the moment equation, which is m equals force times our perpendicular distance. Because we already have all these values given to us, from here on is just simply plug and play. So we can put our values here, such as the distances and the force acting upon it, into our moment equation. And then once we get our three different moments, because we have three different forces acting upon each other, we can then add all of them together to get the sum of our moments. And then our forces, we can just add the given ones that we have.
All right, Vinny, let's apply everything now.
All right, so now that we've solved for AX, we must solve for AY and BY now. To do this, we have two equations, the sum of all forces and the sum of the moment, A. So here we have the counterclockwise movement, which is positive, so that we can have AY and BY be positive. Because 800 and 1600 are the downward forces, we put them as negative values. However, in this function, there are too many variables, so we must solve for at least one variable. We will solve for the sum of moment A. So here, AY is 0, and here we have 800 plus times the distance, 30. Here we have 1600 times the sum of both distances, 30 and 50, and then we have by times the sum of all distances. And we must all equal it to 0. Solving it algebraically, we get that by is equal to 1266.6. So simply all we need to do is plug by back into forces equation. So solving it algebraically, we get that ay is equal to 1133.4. All right, so are we done now?
Actually, we still need to verify all of our results. So in order to do this, right, we can create a test point that we'll label C. We'll plug in all of our known values times their relative distances, and from there, once we solve everything algebraically, we know that C comes out to be 0. Alternatively, right, you can also solve it by doing the sum of the forces that are acting downwards plus the sum of the forces that are acting upwards. It'll be negative 2400 plus 2400, which is 0, which means that equilibrium has been satisfied.
All right, finally we're done. Can I get back to my pool game now?
Yeah, sure can.
Yeah.
Good luck.
I don't need his luck. I don't need no punk teacher to tell me what to do.